let me just start it because so that uh, yeah. And I hope nobody has any objections to being recorded as such. If you do, you can always uh, turn off your video, but it helps me to be able to see people. So, okay, let's see. So okay. Mm, okay. So people can ask, people can watch on YouTube, and they can like ask questions on the chat there or on WhatsApp or whatever. Okay. Hi Bharatendra, can you turn your video on if you don't mind? Uh, if you don't have any objections to being on YouTube live stream.
Yes, sir.
Hello. Okay. All right. So presumably none of you are fugitives from justice. So it should not be a problem. Okay. So good morning, everybody. Thank you to all 6 of you for coming for this tutorial class. And let's begin with somebody who had questions.
One door close now.
So who had that question? Was it Shashwat? I forget.
Just 1 second, sir. I think my problem.
Yeah, no problem, no problem, no problem. These are the unique aspects of having remote classes.
Yeah.
Yeah.
So my doubt was, if we take an expectation value of a vector, so after it collapses into one of the states, one of the eigenstates, do we have to update the probability because we have found it in that state? So
you asked this question, I think, on YouTube or something. I forget.
Yeah, that's the question on YouTube.
Yeah. So okay, so Shashwat's question is basically that, look, you have this state vector, right? And it's whatever, something like this. Okay. And you perform a measurement, and then when the measurement is complete, it collapses into one or the other of these, right? So then he's asking that, well, after this has happened, then you know that it's in this state or in this state. So then don't you have to update the probability? And the fact is that it's true that what you're asking. So this state I should call before, okay, meaning before measurement. And so after measurement, the system is left in or this with probability 1. So this is the correct statement. That so when the collapse happens, when the measurement, you perform the measurement, collapse happens, so you're left with a system which is in either whichever in some eigenstate with probability 1.
Sir, is this discontinuous jump is accepted among the scientific?
Is what accepted amongst whom?
Like, if we don't observe the state, we say that it has a probability proportional to the constant that is multiplied by the eigenstate. So this discontinuous jump in probabilities from the modulus of the complex number to 1, is that accepted? Because it feels a bit hacky to me.
Accepted by whom?
Like the people in the scientific community, like people who are studying this.
Well,
people who came up with this,
yeah.
were they happy with this?
No, nobody's happy with it. Nobody's happy with it, and this is actually the the key question in quantum mechanics. Like I like one thing I emphasize in I've been emphasizing in all my classes is that quantum mechanics is still very much like we are still in the process of understanding it, and so this is one of the things which so this sort of approach to quantum mechanics is known as the Copenhagen interpretation. So in the beginning, in the early days of quantum mechanics, so there were two people who were very influential, right, in terms of um, their like standing amongst their peers, and those two people were one was Bohr, okay, and the other was Einstein, and right, Einstein was influential because he explained the photoelectric effect and so many other things, right? And he first made the idea of quanta uh, concrete, right? So and then Bohr was one of the big guys. Why? Because of his model, right? Because of the Bohr model.
Role model of the
So the Bohr model was the first application of this quantum philosophy, you can call it, to understanding atomic structure, right? So now Bohr's model was not based on like quantum mechanics because this was in 1911, okay, and in 1911 quantum mechanics had not yet been invented.
Yeah.
It was invented in 1925 onwards. So, but Bohr was influential because, well, he's one of the original people who applied it in any way. So Copenhagen is in Denmark, right?
Yeah.
And Bohr was a Dutch fellow, right?
Yes.
Danish, whatever, something like that. So the Copenhagen interpretation was pushed by Bohr. Okay. And Einstein was never happy with it. Einstein was because he did not like this description of reality, if you want to call it, of physics, in terms of some process called collapse, which you cannot control,
Yeah.
right? Or which you cannot describe. So it's like collapse. What is this collapse? Like there is no mechanism for this collapse, right?
Yeah.
It's a completely mysterious thing, right? We don't have any control over this collapse. We don't know what causes it, right? So yeah, so this is one reason that there was a big debate between Einstein and Bohr. And at that time, Bohr's philosophy, the Copenhagen interpretation, became the more widely accepted view simply because it was the one which allowed people to do calculations. It allowed people to do something, but it didn't really answer the key question.
Yeah. Why it collapses.
Exactly. So then over the past 100 years, see, many people have tried to come up with explanations for collapse. So there have been all sorts of theories. There is like let's see. people have tried to construct theories for collapse. So they have one of the key properties of quantum mechanics is that quantum mechanics is a linear theory, completely linear theory, right?
Yeah.
Because it's built on vector spaces and linear operators. So everything that happens in quantum mechanics is linear, except for the collapse.
Yeah.
So people thought that, well, if you introduce non-linearities in the description of quantum mechanics, in the dynamics of the quantum mechanics, so they thought that these non-linearities can introduce quantum mechanics collapse. So there are the most common one goes by the name of GRW, Gerardi Rimini Weber. Then there are other ideas that somehow gravity causes the wave function to collapse. Okay, this is what a lot of people have pursued over the years. Then a third one is that in some way consciousness has something to do with this. Consciousness and it is referred to as, so this collapse is also referred to as state reduction. Right, the state reduces down to its one of the eigenstates. So this idea was primarily pushed forward by Roger Penrose. And Roger Penrose is not some crackpot, okay? He's one of the most,
The Penrose
he's one of the
diagram.
greatest physicists of
Gravity extensively.
Yeah. So this idea is also originally from Penrose, but others also. So yeah, we don't at the moment like have a very good. So this is, all of this falls under the umbrella of something known as the measurement problem. And this is one of the unsolved challenges. There are many people who are perfectly happy with this Copenhagen interpretation. They think, well, that's it. You don't need anything. You don't need to explain how collapse happens. But there are many like me and many others who feel that no, there is an issue. So this has led to many different interpretations of quantum mechanics. Okay. So right now, like we have, for example, the orthodox quantum mechanics. Okay. So orthodox quantum mechanics means this thing, the Schrodinger equation. Okay. And you can apply the Schrodinger equation in both finite dimensional and infinite dimensional cases. But there are other formulations of quantum mechanics. One is known as the many worlds interpretation. Now this is kind of like out there in a way, even though like many people, serious people subscribe to it. The idea is that every time there is a measurement, the state of the entire universe branches out into a different possibility. So in the sense that, so here, if there is a person who performs this measurement, right? So now you can ask, well, one can either measure 0 or 1, right? So how do you explain both of these possibilities? So the idea is that you have some observer. There is a certain branch of this wave function in which this observer says, oh, it's zero. And then there's a whole different branch of the wave function. There's a wave function of the universe in which this observer says it's one. And both of these exist in some sense, you know. So, but this has a lot of issues, and but it's called the many worlds interpretation, because it's like, you know, there are like an infinite number of worlds. So. Then there's also something known as de Broglie-Bohm theory. So this is not Bohr, it's Bohm, David Bohm. So they came up with David Bohm came up with a completely different set of equations which describe the same quantum phenomena and give all the same explanations for everything. But so this, you know, there are many different camps. Then very recent, somewhat more recently, in the past like 10 years or so, so there is a Dutch physicist called Tahoe, and he is also again no lightweight. You know, he won the Nobel Prize for work he did as a graduate student about 40-50 years ago almost. So he is of the opinion that you can understand quantum mechanics as coming from a cellular automaton. Anyways, so these are all okay. These are all like, you know, things which sort of I'm mentioning in case people are curious about such things.
Is the study going on for each field?
Huh?
Is the study going on for each interpretation? Are people trying to prove their interpretations till now?
Of course, it's a survival of the fittest, right?
Yeah.
Yeah, which reminds me that there is a fifth way of thinking about it, which is actually based on the idea of survival of the fittest.
Oh.
And it's called Darwinian quantum mechanics. And primarily it has been developed by Austrian physicist called, his first name is very difficult to pronounce, so stick with Zurek. So he is, you know, he says that, well, you know, quantum states also like have a they
have a natural selection.
They have a natural selection, that's right, and those states survive, which are the most robust in some sense.
Crazy.
Yeah.
So
anyways,
what about path integral formulation?
Whose?
Path integral.
No, but path integral is not, there's nothing controversial about path integral. See, path integral is part of the orthodox approach only. So Schrodinger equation, and you can also say plus path integral. There's nothing as such controversial about the path integral approach. It's just another way of stating quantum mechanics. Right. So anyways, I should, I suppose, try to focus on questions related to the course, right? Or whatever. I don't, people can ask me whatever they want. So,
Sir, I had a question actually.
who, Rakshit?
Yeah.
Yeah, go ahead.
Sir, you said that all operators are represented as matrices, right?
That's right.
So could you just give an example for an operator represented as a matrix?
Well, I mean, I've already given you examples of like angular momentum and sigma z and sigma x, right?
Yeah, but can we write any differential operator like d by dx?
Okay. No, so that's a really good question. So the question is, matrix representation of differential operators. Okay. This is basically, so I've told you about the finite dimensional and infinite dimensional uh, cases, right? So in the finite dimensional case, so if we like, for instance, consider a chain of atoms, and we talk about an electron, and this electron can, it can hop from one side to another, let's say. So then each one of these sites is labeled, let's say 1, 2, 3, 4, 5, and this thing, what do you call it? The position of each one of these sites is like given by x of I. So then we say that there is a state x of I for the electron being at the ith site. Okay. So that's what this state means. So then we have a position operator. Okay. So this is my basis of orthogonal eigenstates, right? So if I have xi, xj, and I take the inner product, I get delta ij. Right? That means basically the electron, if it is in the state x of I, it cannot also be in the state x of j. Okay. So these are the orthogonal eigenstates. But in general, an electron will be in some superposition of these states, right? Let's say 1 to 5. Right? So this is a finite dimensional Hilbert space. So if I have a state, for example, let's say C1 x1 plus C2 x2, right? That this means that the electron is in some superposition of being at the first site and the second site. Okay. So now I have an operator which is which acts on these states, the position operator. So the position operator acts on this eigenstate, and it gives me the eigenvalue is just the actual position. Okay, the position of that, the x coordinate of that atom in whatever coordinate system one is using. Okay, so for example, if I take this position operator and act on this psi state that I wrote down here, then what will you get? You will get C1 x1, then this, plus C2 x2. Okay. So this is obviously not a position eigenstate. This is not an eigenstate, right? Of x hat, this whole thing. So obviously x acting on this state will not give me a, it gives me something. I can't write this as some number times psi, right? So psi is not an eigenstate. Okay, so now what about the infinite dimensional case? In the infinite dimensional case, what do you say? You say that you have some real line, okay, and you can have an electron which is either like in some finite region, let's say plus L by 2 and minus L by 2, okay, and so we'll say that so this is the what is known as the particle in a box. This is the thing that you study in your first year of BTech in our institute. So here the electron's position can be anywhere between L by minus L by 2 and plus L by 2, right? But there are an infinite number of points, right? Why? Because this is a continuum, right? So there are an infinite number of points. So if I have any two positions, x1 and x2, right? No matter how close they are, then there exists a third position, x3, right? So this symbol means for all, this symbol means there exists such that x1, x3, x2. So x3 lies between x1 and x2. So here in this case, how do I write down the state of my system? So this is what you learned in your first year of quantum mechanics, right? You were shown this state psi of x, and you were told, well, this is your wave function. So to speak, okay. But see, if you look at this kind of an expression, you see that on the left you have the state psi, but the state psi is not psi of any x, it's just the state psi. What are these positions x of I? They are the eigenstates, okay. So again, in this infinite dimensional case, we can set up our eigenstates, but now I don't have any I index. I don't have an I index, right? Because it's an infinite number of states. So I have x, and then I can have a different state, which is, let's say, x prime, where x prime is just a different point from it. And then if I take the inner product of these two states, what happens? Here I get, when I take the inner product of xi and xj, I get delta ij. Now delta ij is a Kronecker delta, right? It's a matrix. When I take the inner product of these two states, what do I get? I get delta x minus x prime. Where what is this delta? This is called the Dirac delta. And this is not a discrete function, it's a continuous function, but it's something known as a distribution. Now, if I want to write down a state, some state psi for this particle, okay, then how should I write it? Well, it will be some superposition over all my position eigenstates. Now all my position eigenstates are just labeled by the position, right? X. But instead of a sum, I will have an integral, right? Because X is a continuous parameter. And now my coefficients will become some function of X. And this is how I will write my state. Are you following this so far, Rakshit? Right. So now I can ask again, what is the position of operator acting on this state? Well, the position operator acting on this state will give me the same thing, C of X, but now the position operator acting on this X eigenstate will just give me the number X times dx. Okay. Okay. Now, so this is fine, right? So this is just a vector. What kind of a vector is it? It's an infinite dimensional vector. Right? Because each one of these positions X, each position X is an individual eigenstate. And there are an infinite number of these positions. So now you can ask, for example, what happens if you want to find the expectation value of this operator X. So if you want to find the expectation value of this operator X, what would you do? You would take psi X hat psi like this. Okay. Inner product of this thing. But before that, how do I write down the inner product of two states or one state, whatever? Well, before that, how do I write down this bra state? So the bra state is actually nothing but the complex conjugate of the ket state, right? So these coefficients, they become complex conjugated, and then these states I write as X. Everything else is the same. Okay. Now, then one can ask, well, how do I take this inner product? Psi. Okay. So the bra state is C star X. Okay. And the ket state is C of X. But now you have to be careful. You're summing over this X parameter, no? Right? You're integrating over X in this expression. So here you have to use a different parameter. You have to say X prime. You can't integrate over the same expression twice. Okay. So you get a double integral. And what do you get? You get C star X, Cx prime. And then this bra vector in a product with this ket vector. Okay. And then this double integral. But now what is this quantity? This quantity is delta X minus X prime. Okay. Now, this has the property that when you integrate some function with this, basically it will just pick out that one value of X. So you can perform the integral over X or over X prime. You will get the same answer. You will be left with this answer at the end. The integral will just pick out this value of X. meaning all the other x primes will vanish, only we will be left with it. So you'll be left with c star x times cx. That gives you c of x norm squared dx. This is the inner product of the state with itself, okay, in the continuous case. And if you remember, this looks exactly like the discrete case, right? In the discrete case, what would you have? You would have I is equal to 1 to n c of I squared. Here you have exactly the same thing, only it's an integral. Now, I haven't exactly answered your question about the matrix operator. So let me do that. Okay, let me just do that quickly. If you want to find the expectation value of this, yeah. So I mean, well, your matrices become infinite dimensional. Okay, basically, see in the finite dimensional case, your matrices were finite dimensional. I goes from 1 to n. J goes from 1 to n. In the infinite dimensional case, what happens? This is finite dimensional and then infinite dimensional. Your operators now become, they look like this, where x and x prime, they are continuous variables now. So if you want to take, for instance, this state and act on psi, how should you do that? You do it like this: a of x comma x prime times c of x prime get x prime dx prime. Okay, so I mean, if this doesn't like make complete sense to you, don't worry about it. Okay, at the moment, I mean, this is just to like sort of give you a taste of the general thing. But the point is that, see, the finite dimensional picture makes one thing completely clear, that your quantum states are vectors. The infinite dimensional picture doesn't, like, I mean, it's not, it's clear if you know vector calculus, if you know about vector spaces, infinite dimensional vector spaces, then it's okay. But most people don't know that, that for example, if I have some function of x, okay, f of x, any function, let's say exponent x or x squared. Now, what if I told you that these functions are all vectors? You'd be like, huh? What do you mean they're vectors? How can this function be? Well, you think of f of x like this. Instead of writing it as f x, think of writing it like this: f subscript x. So x is the index of the vector, and f is the name of the vector. Okay. So for each point on the real line, the component of the vector at that point is what? That component is just the value of that function at that point. So now I can have two different such functions, and I can ask now, what is the inner product of these functions? Okay. I can ask, what is the inner product of g and f? So what will this be? This will be g star x f of x dx. So if you think about this in the discrete case, what would it be? G of f would be G of I star f of I, right? It's exactly the same thing. Only difference is that now here I is your continuous discrete variable and here x is your continuous variable. So this is actually the basis of when you work with the Schrodinger equation, and when you say that psi of x is a solution of is your wave function. What is the meaning of psi of x? Psi of x is, you should think of it as psi subscript x. So your state is actually psi. It doesn't make any reference to the x. Psi of x is the, you can think of it as the x component of the state psi. So x is an index. So this also, I mean, then there are other things that this makes it clear. But again, like, you need to be, you need to feel comfortable with, like, vector spaces and in calculus and all. If you are not like confident, then you will have some issues. So yeah, does this answer any of your questions, Rakshit?
Yes, sir. Thank you.
Rakshit is like, क्या पूछा था और क्या मिल गया?
No, but I got an idea of what you are saying. So yeah.
Right. Okay. Okay. Then Shoboj had a question in the chat. He had said, "What about decoherence?" That's a really good question, Shoboj. We'll talk about it at a later point. Okay. It's already like 8:48. Utsav is asking, C of x is of the order x of n. What do you mean by is of the order x to the power n?
So like I want to know that Cx is like if it's to the power x to the power n of the order, like it contains x to the power n.
Do you mean like something like a polynomial?
In the equation, in the state equation, like psi equals C1 x1 plus C2 x2. So are C1 and C2 also dependent on X and they are of one order higher than what is Cx?
I don't think I follow.
Cx dx, right?
Huh?
So in infinite dimensional,
your voice is
integrating Cx.
Your voice is breaking up.
So I'm asking that in infinite dimensional, we are integrating Cx dx, right?
Sure.
So this will the discrete value Ci, like it's if we are going with the analog, then it will give sigma Ci, something like that.
Sigma sum over the I.
So I think he's talking about the units of C of x.
1 second, Shoboj. Is that what you're referring to, Utsav? Are you talking about units? Shoboj, that's a big no. It's a capital no. Okay. Well, so I'm not sure what he's asking, because one thing is that your internet connection is also a little bit laggy. Sadly, because everybody is sitting at home and watching Netflix these days. So yeah. Do you want to try again, Utsav? Do you want to try to like ask that question again?
Sir, if we are integrating CX dx, we will get sigma C1, sigma CI, right?
If you are integrating CX dx, that's what you're saying?
Yes, sir.
Then what will you get?
Sigma CI, like in analog.
Sigma. Okay.
So,
You mean the discrete case? Fine.
yeah.
Fine.
So, is this sigma CX, like is CX of one order less than CI independence, like CX is something like DCI by DX? Is it something
No.
like that?
Yeah, I mean, no, I mean, this is just like going from discrete to continuous, right? So when you perform an integral, when you perform an integral, for instance, okay, so this is, let's say x, okay, and this is your function, whatever. Okay, now what do? I take my domain, which is x in this case. I take it and divide it up into so this is right, called a Riemann sum. Then something like this, Riemann something integral. So so what do? I divide up my domain into n discrete sets, right? So I is equal to 1 till n, and then I can approximate this C of x, this integral, as sum of C of I times delta xi. That is, C of I is the y coordinate and delta xi is the x coordinate. So it's the area of this thing. Now, so this I can write as summation of C of I. Delta x I can write as my delta x of I can write as the total interval I have, whatever it is. Let's say this length is L. Okay, and let's say I'm dividing L into n segments. So then I can write this delta of x of I as L by n, assuming that all of the segments are equally spaced. So this becomes L by n times sum over C of I. So if you want to like make the direct comparison between the continuous and the discrete case, then you have to have a factor of this form.
So is the state x dependent on x dx?
That's a good question, right? That's a good question. So this is why when we say that you have a state, when we say that you have a state, this x, ket x or ket x prime, and the inner product of this state with another state which is even infinitesimally away, right, is still going to be 0 unless and until the both of them coincide. So this inner product is expressed in terms of this delta function. This delta function has the property that it's equal to 0 but it's not a it's actually a function. So it's a function which is like, which looks like this: 0, 0, 0 everywhere. Then there's a very sharp peak, and then 0, 0, 0 everywhere. And the sharp peak is exactly at the point x is equal to x prime. And it's an infinitely thin and infinitely thin peak. So this going from this continuous to discrete case, there are some things that one has to be careful about. Your question is, does the state depend on this d of x? And the answer is no. I mean, because we are well, I mean, it's an approximation, right? Going from continuous, from discrete to continuous, you are making an approximation. So you lose information when you do that, but that loss of information is very less. So because you know, you can control that by so this is what happens when you do, for example, numerical integration, right? In numerical integration, a computer doesn't calculate integrals, right? It calculates sums, and it calculates sums by exactly this process. It calculates sums exactly by dividing your domain into finite intervals and then summing over them. So this is not exactly equal to this, right? There is some numerical error which comes from having a domain of finite size. But by making the domain smaller, you can reduce that numerical error as much as you want, right? So that the right hand side, this expression becomes as accurate an approximation for this as you want for the left hand side. So it's the same thing for when you write quantum states, because the underlying math is just this. So you have a quantum state, whether you think of it as a continuous state or a discrete state. The discrete state can be made arbitrarily, an arbitrarily good approximation to the continuous state. I don't know. I hope that answers your question. I'm not sure it does, but I hope it does. Okay, and I'll stop it here for today. I think. And we didn't really like talk much about the actual course so much as other things. But anyway, the point is to clarify your doubts. So I hope I've clarified some of your doubts. If you have more doubts, you please put them on Moodle, okay? So we can all have a nice discussion. And Kushal and Aditya, I hope you all, you know, were following. If you have any follow-up questions, you can always put them on the Telegram group, or you can put them as comments on the YouTube video, or you can, you know, whatever. Just use your telepathic capabilities to try and contact me. It might work. You never know. Okay. All right. So I'll stop it here for now.